Okay, here's section 2.3.3, phase portraits. And these are just a simplification, really, of the direction fields because we use these with autonomous ODE, okay, ordinary differential equation. And so the whole thing is, if I have an autonomous ODE, something like, just let's take u prime equals 1/2 u, then notice is, if I take some values of t, some values of u, and some values of u prime, then, and we'll just do a couple to get the point across, t equals 0, t equals 0, t equal 1, t equal 1, u equal 0, u equal 1, u equal 0, u equal 1, then we'll get a 0 here for u prime, and then a 1/2. But then notice at t equal 1, we get a 0 and a 1/2. Okay, because it didn't depend on t. If I went to 2's, right, and a 0 and a 1 here, it only depends on u, so I would get a 0 and a 1/2. And so if I were to go over here to start drawing our direction field, I guess I can't talk and make dots at the same time. What I would see is, all of these down here where u was 0, so here's t, here's u, those are all flat because we had an equilibrium there, a value of 0. And then these would all be at a 1/2. They'd all look the same. So see, all I really need to look at is, say, something along the y-axis. Now, your textbook kind of draws them both directions, both vertically and horizontally, these phase portraits. But let's look at this one, okay? The way we would do the phase portrait is we would find the equilibrium. And in that case, that was, u prime equals 1/2 u. Set it equal to 0, we got u equals 0. Okay, and then, just like in the good old days of pre-calculus, college algebra type things and all that, you look at the sign of the slope, okay, so in other words, our u prime, on each side of the equilibrium. Now, so if you looked at this as just a single equation, like this was x or something, but you said, oh, I've got 1/2 u equals 0. Okay, so then u equals 0. And you did the old thing of, well, okay, so what is it on each side? Then, I could check, well, if u is less than 0, then 1/2 u is less than 0. Okay, and if u is greater than 0, then 1/2 u is greater than 0. And, I sort of have my choice here. Now, if you do this vertically, because u was plotted on the y-axis, you would go here and you'd say, okay, here's the equilibrium at 0. And then to show direction, yes, I have that nicely done there, okay. Right, this is down, this is negative. Okay, and so what we're showing is not the value of u. The value of u here is certainly positive because it's above 0. But this is u prime, okay? Because we're looking at 1/2 u and 1/2 u. And, oh, well, and so I said that wrong. Sorry about that. Silly me. You know, like I keep telling you, I'm not very good with numbers. So try that again. Well, the problem was I was looking at this one first, and, you know, it's not the positive one. Okay, so sorry. When u is positive, though, then 1/2 u, the derivative, so u prime equal 1/2 u, up here is positive, and so I should be drawing things that way. We'll do a couple more examples to hopefully get it right. And then, you know, down here, u prime is equal to 1/2 u, but it will be negative down here, and so we would draw the direction negative. And so what that tells us, if I were to draw a slope field or direction field, you know, here's t, here's u. Now I'm actually going to put 0 up here so we can see it better. But that's an equilibrium. If u is equal to 0, it just stays at 0. However, if u is positive, what we see are solutions heading up like this because the derivatives will all be positive. And if it's negative, they'll all be heading down like this. Okay, and so we're going to get into this more in the next section, but this is an unstable equilibrium. Okay, because if I'm at 0, it will stay 0, but if I'm just a little bit off of 0, it's going to move off of 0. And again, we can see that if, you know, if, well, of course, now I just realized something else is, you know, I was using this k, oh no, I did use 1/2. Yeah, sorry. Okay, so we had u prime equals 1/2 u. Now, what I know is that implies that u is equal to some c e to the 1/2 t. And I know that function. And if c is greater than 0, so in other words, if I am up here somewhere, so that I've got that positive value of c, then I know this function does indeed grow off to infinity like that. And on the other hand, it will head down like that if c is less than 0. And, you know, in this case, you know, u is always going to be greater than 0, and u is always going to be less than 0. Okay. And so, you know, that's what's going on. Sorry I got those directions backward, but let's do another quick example. In the last video, we had u prime equals, say, u squared minus 1. Well, if I set that equal to 0, all right, I get that u minus 1 times u plus 1 equals 0. So u minus 1 equals 0, or u plus 1 equals 0. And so that tells me, well, let's get that to show up. Okay. So that tells me u equals 1, or u equals -1. And so for this phase portrait, I can just draw it over here since I'm doing it vertically. There's 1. There's -1. Now, what happens in between, right? If If I am between -1 less than u less than 1, what happens? Well, let's use 0. That's in between. That's easy enough. I get a negative value. And so that says I should draw an arrow that goes down like that. If I have a number u that's bigger than 1, if I have u is bigger than 1, then the derivative will be bigger than 1, and I create an arrow going up like that. And if u is less than -1, then u squared will be positive, and I'll get a positive out of that. And so that will be positive. And so what I can see is that this will have solutions heading toward it, like so. So this is going to be stable. But this has things heading away from it, like so. And so this is unstable. And that's the idea. So the mathematics involved really is just before calculus. It's pre-calculus stuff. It's stuff you had to do in algebra classes and all that. And that's all we're getting at. And you know, that characterizes then what our solution may look like, you know, for different values. So again, if I, you know, had an initial condition in this case of like 0, 2 for u, then I would know that this solution headed off like that. On the other hand, if I had an initial condition of 0, say 1/2, then what I know is this solution should head down like this, but in particular, it should head toward a horizontal asymptote of u equal -1. And so from an autonomous equation and these phase portraits, you know, I can learn a lot about at least the long-term behavior of a solution to a differential equation without having any idea necessarily how to do its antiderivative. Okay, so there we go. That's phase portraits.